Okay, so I'll take that for yes. Yeah, okay, cool. Thank you. Okay, so welcome to another Friday. We are almost getting to the end. So this is the agenda today. We'll again have part A and part B. Part B is a little bit harder, and there will be a little bit of a fudge in order to go through these things, because we haven't really covered analysis and let alone differential equations. But hopefully, the way I organize stuff, you will be able to get to the point, which is really the unitary evolution stuff. Okay. But before we start, I want to thank you guys. You made my day. My week was going terrible until I got this thing. So thank you so much. I hope I didn't forget to highlight any of you. I think some of you have like signatures and these things, so I had to ask Amir. So thank you so much. It's here, and I will make a great use of it. So thank you so much. You made my day, huh? In fact, you made my week. Yeah, no problem. So thank you, everyone. Really appreciate it. And thank you, Amir, for organizing all this. And if I forgot to highlight anybody, please let me know so I can thank the person too. But yeah, thank you to everyone anyway for attending and listening to me. That's already a great thing for me. So yeah. Okay, so going back to the foundation module. So we are in session 3 of 4. I haven't decided yet whether I should have something extra. Let's see how it goes this session and then maybe the next session. But I would have thought that perhaps we can just wrap up the foundation module, and then any extra thing that I wanted to do, maybe I can just share some extra material that you can catch up with, because then in the advanced module, we will, review the axioms, we will review some of the stuff that we have been going through, but in a much more generalized way, covering, infinite dimensional Hilbert spaces also. Okay, so it's not just finite dimensional stuff like we've been focused on foundation module. Okay, so yes, I did like it. So thank you so much. Yeah, don't worry, Stefano. That's fine. Okay. So where are I? Yeah, does anyone have any questions about this, about the wrapping up of foundation module so far? Okay. Yeah, so nobody, in fact, let me enable the Q&A just in case. Later, we can come back to this later anyway, so don't worry. Okay, so let's go to part A. I forgot. I knew it. I had like a typo somewhere, because I meant to have like a quote from Paul Dirac, but I forgot to remove Professor Susskind's quote. So there you go. The first error. So this is not Paul Dirac. This is Susskind. So I will correct this. I will add what I wanted to share from Paul Dirac. Okay. So let's just go through some key remarks before we kickstart. So the first thing I want to say is, obviously, in the previous session, we learned that hermitian operators are diagonalizable, right? Which means, you can find a unitary. They are diagonalizable by unitary. You can find a unitary U and the diagonal matrix so that the hermitian, can be decomposed this way. Okay, and we also commented. I hope you could find this or manage to put it together by going through the study materials. The eigenvectors of A coincide with the columns of this unitary U that decomposes the operator, and the eigenvalues coincide with the diagonals of D. Another time we commented after going to the axiom 3, I believe. is that it can be proved that for finite spectrum, because we are dealing with the finite dimensional operators on finite dimensional Hilbert spaces, when you have an operator, Hermitian operator encoding an observable, you can derive from that, from the general principle in axiom 3, you can derive that the only possible measurement outcomes are the eigenvalues of A. Okay, this is because we are dealing. This is not true. This is not the case when you deal with continuous spectrum. This is just for discrete spectrum in this case, because we are dealing with the finite dimensional Hilbert spaces. Okay. Another thing, I think, I don't think I commented on this, but maybe this is more of a thing to ask a physicist, because I'm not sure. I believe, according to physicists, is that the eigenvectors of a Hermitian operators, remember, they form an orthonormal basis. They represent states where you can make measure, where A can be measured without uncertainty, I believe. Okay, I know we haven't talked about uncertainty. Maybe next week we will talk about it. But yeah, so but I would ask you to ask a physicist. Maybe our friend Soham could help us if he's around. Let's see. Is he not? Yeah, it's okay. It's fine. Okay, so another thing. Very important is, obviously, this is how we defined the notion of a unitary, an operator being unitary. It satisfies this, so it's the inverse of its own dagger. But alternatively, using the inner product, because after all, the Hilbert space has an inner product, right? So the unitary essentially preserves the inner product, which also means it preserves the norm. So it does not change the thing. So therefore, this is why physicists choose unitaries. This is why they become the symmetries for quantum theory. Okay, what all that means, if you go through the perhaps physics class, they will probably tell you more about this. But yeah, this is an alternative way of defining a unitary operator. Okay, so I was saying axioms. So we have gone through these axioms. So if you are just joining us, if you haven't seen us go through this, I recommend you to go back again to few lectures back. So the last session we gave axiom 3, which is the axiom related to measurement, right? So today I will hit you immediately with the axiom 4. In fact, let me check. There is no question so far, no comments, so that's good. And by the way, I hope some of you, or at least you try to do the challenge. Did anyone complete any of the challenges of computing the expectation values of some of the operators that the Pauli operators in this case? It's not a problem if you didn't do that. Maybe you already know how to do it, and it's like just a toy stuff, so that's fine. Let's dive into axiom 4. Okay. So here's axiom 4. First of all, let me make a comment, like we did before we laid out the other axioms, is that there isn't a canonical way of expressing the axioms of quantum mechanics, really. So different people will express it differently. I'm certainly not a physicist, so I'll probably not express it the same way as physicists do. But nevertheless, I will go through what I mean with the axiom, what I want to convey with this axiom. So it says, provided the quantum system is undisturbed, so that means it's isolated, nothing happening, you're not making any measurement and these things, you leave it alone, okay? Then the system evolves smoothly over time, t, okay? So time is a real parameter, according to this equation, okay? Where H is an Hermitian operator encoding the energy of the system. In this case, it's called the Hamiltonian, Okay, so the axiom is telling us that so far in the other axioms we've been setting out the kinematic aspects of the theory. This is now the dynamical aspect of the theory. So this is telling you how the states, evolve over time when you are not doing anything to the system. Okay, so you leave the system alone, you're not doing anything. This is how the system evolves. This is known as the time-dependent Schrodinger equation. Okay, I know you are all very curious. You will be asking, what's the difference between this and time-independent Schrodinger equation? This module is not to a place to talk about that, but I recommend you actually to ask a physicist or perhaps do some research to see the difference. But it's something that we will cover in the advanced module once we have the language to be able to discuss all this. Okay. One thing also to note is that physicists take the convention of setting the h bar, which is the Planck constant. I forgot to mention it there, but it doesn't matter. Most of you, I know, already know this, to 1. So therefore, the equation becomes this. The Schrodinger equation becomes this. Okay. So now the question is, for practical purposes, if we are giving an initial state at say, I'm using time 0 just to make it easy. I could have used say time t prime or something, but it doesn't matter. This is much more intuitive. So how do we find out the state at a later time t? Okay, so part B will be to give you the toolkit, or at least to show you how you do this. Okay. It might be a bit, for those of you who might not being exposed to analysis or even differential equation, that's fine. You can just go through. And this is actually, I'm not expecting you to know any of that, because in this module we haven't covered these things. Okay, but hopefully the way I set it out, the algebraic aspects of the approach that we are taking will still enable you to see how this thing works. Okay, so let me check the chat. Okay, so Amir is saying is a good. It was good practice. Yes, that's a good thing. Okay, so we have a question. In Dirac notation, it is a case to swap the. Okay, I think I will come back to your to the first question later, Amir, just so I can look at the notation. I struggle without LaTeX to see, especially when you are saying about the Dirac notation, because I'm starting to think, as you know, as a mathematician, Dirac notation is like, okay, the second one. Yeah, H is Hermitian. Yeah, so I can start answering this. So H is Hermitian. Remember the thing, because it has to, because the Hamiltonian is an observable of the system, right? So it has to be Hermitian, not necessarily. But now you will in the next session you will see then why unitary operators play a very important role indeed. So it's not unitary, but it will lead us to unitary operator. Okay, so. I will leave it here. You will see what I mean once we get there. So I have another question from our friend George. Are different axioms equivalent? Yeah, well, I mean, in terms of the I'm not sure if axiom is the right way to put in these quantum mechanical stuff. I'm just using it axiom because this is a mathematical driven stuff. People normally say, maybe the appropriate thing is less stronger is probably postulates. This is what physicists normally use. So, it's not axiom in the sense of having an axiomatic system in the mathematical sense from that point of view. So, yeah, you can say that the quantum axioms that different people express one way or the other, they lead to the same thing. The only thing is some axioms, some people express them in a very general way that others have less general way of expressing them, and some stuff that can be derived from more general axioms are also taken as axioms. Okay. For example, you will see that if you, I think I recommended the lectures of Professor Susskind. You will see the way he puts the axioms of quantum mechanics. Some of the stuff are not really axioms because you can derive them from general principle, more general principles. So mathematically, an axiom cannot be derived from another axiom because an axiom is an axiom. So yeah, I don't know if I answered the question, but I hope I'm at least closer to answering the question. We can feel free to ping back again on this. So Nikolai, phi was it's now a function. Yes. So this let me put the thing. Yeah. Yeah, move to the question. Yeah, so this is very interesting. It takes you back to the roots of quantum mechanics, to the wave mechanics, where the wave function. So the Schrodinger equation kind of originates from there. So when Schrodinger wrote his equation, it was just his wave function, really. So it's a function indeed, but we have taken that because that can take an abstract form in a Hilbert space. So it's therefore, it's a vector. So it's a parameterized vector, if you will, if this is in a nutshell. Yeah, but you will see what I mean. I guess once we get to the solution of it. Okay, so it's just essentially we parameterize the vector. Okay, so we parameterize it with the real number. So view it like that. With time, with something we call t. We can do that. This is where it becomes, I understand it becomes a little bit confusing because the thing, as you go along, as you take more things into consideration, because so far we've been just taking into consideration the kinematic aspects of the theory. So, but the dynamics is also, very important, right? You want to know how the system evolves. Now, another thing, this is not too mistaken. Let me just comment on this because this might be a bit confusing, and I hope I'm not, apologies to the physicist on the audience, I'm not getting it wrong. You will see, obviously, this does not mean that, the probabilistic nature of quantum mechanics is not like, it might sound like a contradicting stuff. This is telling you how to find out a state, what the state is. It doesn't tell you what you get when you do measurement, okay? So this is not this is just telling you if you have an initial state, then, what's the other, the state at the next, at a later time t, okay? So the probabilistic nature of the theory are still preserved, okay? Okay, so I see we have a lot of other questions. Okay, so I will come back again to the Q&A just in case. Okay. Now, one thing I want to refresh, because I think today we will remind ourselves what as in mathematicians don't use this the thing, but this is the language of quantum mechanics. If you want to say a times b equals b times a, you say they commute. So you use, that's why I'm using this. Okay, so I assume all of you from the sections on ring theory or something, we went through all this. I think there's probably a typo somewhere. I hope not. So if you find it, I think our friend at the TA is a champion of finding my typos. So if you find any, just let me know. So anyway, I believe you already gone through this. If not, it's an opportunity for you guys to review, especially in the context. Imagine if these operators are Hermitian, for instance. Okay, and in fact, I'm asking here if the commutator of two Hermitian operators is Hermitian, and also if we multiply I times the commutator of the Hermitian, is that Hermitian too? well, we don't know. You have to do the calculation. And I would encourage you to do even for 2x2 operators. Okay. Another thing, this is, I didn't want to hit you with this technical detail, but since we are talking about commutator, I thought it's very important for you to at least to say this. In most physics textbooks, say when X is okay, so X is an operator encoding position and P encoding the momentum. The canonical commutation relation is normally given like this, but more precisely, it's this. So the physicists, they ignore the I, so they write this. So it's a bit confusing. In fact, I remember in my university days, a colleague was trying to explain me, like, I wrote this, I was like, this doesn't make sense. How can the commutator, this thing become a scalar and this thing? He was like, oh, no, we just ignore the I. I was like, how are we supposed to know? So physicists normally often do this. They assume that people know stuff, but yeah. Anyway, this is the proper way. So this is just a shorthand for this. So they ignore the I on the thing. Now, it's very important to know that this commutation relation cannot be satisfied in finite dimensional Hilbert spaces. So this is only possible if the space is infinite dimensional. Okay. So when you see this, just assume the Hilbert space is infinite dimensional, okay? So therefore, if you want any theory, if you want to build a theory that satisfies the canonical commutation relation, your Hilbert space has to be infinite dimensional Hilbert space, okay? Which is why I guess some of you will know now, see why the reason why Heisenberg used an infinite dimensional Hilbert space in his theory in the first place, okay? So it's something that I thought would be nice for you guys to know. If you see this in the physics textbook, this is only formally this is only true in if the Hilbert space is infinite dimensional. Okay, which is why sometimes when physicists need to say consider the spin of a particle plus with something else. So they would take the tensor product of a finite, say C2 times the space of a square integrable function, which is infinite dimensional. So the tensor product of those two, then you get an infinite dimensional space. Okay, but because in that scenario, for instance, maybe you want to we want to take into account momentum and position of the particle. Okay, so it's a little bit of a technical detail that I wasn't thinking to tell you about this. I don't know if it probably doesn't matter, but it's good to know anyway. So when you see this, you know immediately that Hilbert space cannot be Cn. It has to be infinite dimensional. And sometimes I'm not even sure if some people, in physics and these things, they're even aware of this. So in some of the papers and all these things that people write. Okay. Let me check. There's no question, I guess. Okay, so Soham is here. Let me bring Soham. He's we always like to have Soham on the audience. Before I proceed. I hope I invited him. Let's see. Okay. Okay, I think I'm having problem inviting our friend. Maybe he's not able to join, that's fine. See, it could be also the crowdcast. Okay, let me check the thing. Okay, so, well, last week we covered diagonalization, okay? So, now we want to cover this thing, like what we call simultaneous diagonalization. So when you have two operators, A and B, they are simultaneously diagonalizable if there exists an S standing for simultaneous, I guess, such that these things satisfy. Okay. So this is essentially in a decoding this. This essentially in a way implies that there is a basis in the Hilbert space whose elements are eigenvectors of both A and B. So this is interesting, right? So we know that the eigenvectors, say, for example, if these are hermitian operators, the eigenvectors are basis, are orthonormal, right? So in principle, I don't know if this is useful to physicists. If I were a physicist, I wanted to do something with these two operators. I know they have a common eigenbasis, so I might as well use build my stuff using those two, so I can work with these two operators at the same time. I don't know whether it makes sense, but this is how I'm thinking. Maybe physicists would like to why this is important. It's very nice to have. Now, here's a caveat. So this is telling us that even though it's nice to have it, this property, the caveat is this: they have to commute. So A and B are simultaneously diagonalizable if they commute. Okay. So it's nice to have, but the caveat is they have to commute. Okay. And as a consequence, if we have two Hermitian operators that commute, then they are diagonalizable. So they could become a nice tool to have to build your stuff. If you find two operators that commute, if they are simultaneously diagonalizable, then you know that they have common. You can use their common basis to do whatever you want to do. I guess anyway. I'm just trying. This is where I actually recommend you guys some of these mathematical things to see, for you to start to bridge the gap between the mathematics and the physics. Okay, because we are now talking about operators that are encoding physical quantities, right? So it's always I think as an extra challenge for you guys to try to go and think about these things. Okay, even if you are not going into in physics, even the guys interested in quantum computing, this is all very interesting. I think to start thinking about consequences. Okay. Okay. So Ham is in another meeting. That's fine. So Amir is asking why the comment about Hermitian. Well, I guess this is duplicate from the comment I wanted to make here, that if they are simultaneously diagonalizable, it means they share eigenbasis, right? If that makes sense. From the comment I was making, right? If I was a physicist, I was handed these two operators that I know that they are simultaneously diagonalizable. I know that they have a basis, eigenvectors that form orthonormal basis that on the Hilbert space, right? So I hope that answers the question, or does it add more to the confusion? Is that yes, Amir? Okay, so I will proceed. I hope I'm, in fact, let me ask because, okay, good enough for now. Okay, that's fine. Maybe in the next few slides, you will see other stuff. Now, here's an interesting thing. So what we call commuting family of operators, okay? So you have a set. Let's say a finite set, where n doesn't have to be this n, okay? I don't know why I even added it. I should have probably written k instead of n, but it doesn't matter for the purpose. Let's assume it's n is equals to this. It doesn't matter anyway, but it could be any other k, okay? So this set is called a commuting family if any two pairs, distinct pairs, obviously, that's why I put I different than j, they commute. Okay, so in our case, again, maybe this is Amir, again, another possibly confusing comment, I don't know. I mean, I'm trying to put myself in the physicist's shoes. If I were a physicist, I would probably want these to be hermitian, a family of commuting hermitian operators, right? These are the operators that we are interested in anything, right? Of course, we also want unitary ones, but those will come after in the next session. Okay, and then there is this very interesting theorem. This something that you can obviously find on the study materials and these things. This is so for any commuting family of operators, there exists a ket in H that is an eigenvector of all this all of its members. So that means the operators have at least a common eigenvalue, right? Now the question again is, what could this property be? Would this be of any use to physicists? I don't know. Maybe we should ask our friend Soham and these things. But again, this is one of the things that I will say. Maybe as part of the challenge for you is to go and think about all these properties that we've been covering. What could they yield? Will they generate anything interesting? For instance, even if it's just intellectual stimulus for you guys. But yeah. Okay. And now we have another concept related, as you will see, that this simultaneous diagonalizable family. Okay, so this one is this commuting family. Okay, so to not mistake them. And this one is family of matrices that are simultaneously diagonalizable. Okay, so we say a sequence. Again, the n here, this should have been k, maybe not necessarily related to this n. So sorry for that, but yes, you understand. This is simultaneously diagonalizable if there exists an S such that this conditions is satisfied for all. Okay, so S diagonalizes all the elements of F. Okay. So this means the notion of simultaneous diagonalization, which is what we have gone through here, only obviously we define it for two operators. This can be extended to an arbitrary number of operators, okay? And here's an interesting theorem. If D is, again, you can just imagine this is K, it doesn't have to be N, is a family of diagonalizable operators, then D is commuting family. So this is relating this thing is a commuting family. So it's telling us D is commuting family if and only if it's also simultaneously diagonalizable. So this theorem is establishing a relationship between this and this. This is very interesting, at least mathematically anyway. Now, whether physicists will find this interesting, that's something that maybe you can go and think about. Okay, so thank you, Soham, for answering the question of Amir about the Dirac notation. Yeah, I was afraid of the Dirac notation. I always panic with the Dirac notation because it's a nightmare. It's a nightmare for a mathematician anyway. So you always make a mistake. Okay, let me check. Okay, so far so good. Again, I recommend you to go and start thinking about possible implications of this, right? If these guys are, say, Hermitian, for instance. Okay, so I'm going to go to part B. Let me check the question. I think so far so good. No question. I don't see anything on the chat. So, okay. So before I go to part B, I'll just, as I was saying, for those of you coming late, part B is really, we haven't really developed the language to really go through like the analysis, that we need in order to treat it like in a rigorous fashion. So I will skim through things just in order to go to the essence of what you need to know. The actual we will in the advanced module, because we'll have functional analysis 101, all these things that where we have the deficit because we haven't had the analysis stuff, we will make up for it in the advanced module. Okay. Now, if some of you already know this, or later on, you can go and pick an analysis book or something, a book on differential equations and these things. That's fine. You can catch up and these things, but that's not a problem. In fact, one of the things that I might do after we wrap up the foundation module is to curate some materials on functional analysis, for instance, and a few other topics that we couldn't cover, and share it with you ahead of time. So those of you who have time and want to digest, want to learn in advance before we actually start, you can do that. And then later you can join the sessions to refresh and maybe help on the chat. I don't know. But I might do that for the impatient, for those who don't want to wait until we go through the advanced module in order for you to fill up the gaps of the things that we didn't cover in this foundation module. I'm happy to do that. And in fact, I will do that. I will share some curated stuff on functional analysis that way. Okay, someone, can you back for one moment? I can put up. So which slide, Amir? This one. Yeah, okay. Okay, so yeah. I hope you didn't find a typo somewhere, and I'm pretty sure there will be typos. In fact, another thing I want to say before we go to part B, this is just an idea. It's up to you guys. I'm pretty sure in all the lecture slide stuff, there are like zillions of typos. So it could be some of you, the community members, those who want to refresh particular topics and these things. Maybe it's a good exercise to go and find the typos and then, maybe correct them, something like that. It's a best way to refresh whether you learn something. There will be not just typos, there probably some error or something in the stuff that we went through. I'm pretty sure there will be something in the thing, and this is a way of refreshing just the stuff that you went through to see whether it stuck to your head. So it's definitely something in the gap from after the foundation module is wrapped up to the advanced module starting. This is something that you could do, and maybe you could organize. I know you already have like a channel or something where you engage with each other. Maybe you can, yeah. So, Sohan, do you have any questions? Something you wanted to say? Yeah. Okay. So, let's go. Now, this is the thing. I know this is why I'm saying, we haven't covered, series and these things. So, given a n-by-n matrix, this is why I'm going to skim through this thing. Because we haven't really gone through the notion of series. A lot of you, some of you, the Sohams and these things, you already, all this. This is the thing. So the exponential of A is essentially defined like this. It's this series, and when you expand it, you have something like this. The identity plus the operator, blah 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 blah. It goes on forever. That's why we call this is a series, because it's it can go on forever, right? It's not a finite thing. Otherwise, we call it a sum. Okay. Now you don't need to know what this means, but this is true. This converges for all A in Mn. In fact, part of the reason for that is because this is a Banach space. Okay. This is one of the things I was saying, in functional analysis, you will understand what all this means. But this is good news, essentially. It's telling us this is a good news. Just view it as a good news, okay? And then you have these properties. This is where I'm pretty sure there might be some typo here. So, typo hunters, please, yeah. So please correct. But you can see some nice properties here of this of the exponential. Like for example, the exponential of the negative of the inverse, additive inverse equals to the exponential of the operator, the inverse of it. This is very interesting. And this one also, if A is diagonalizable, so the determinant of A equals the determinant of the exponential of A equals the exponential of the trace of A. Well, this is a real number. This is the thing. You know how to do this, so it's not. You know how to calculate the exponential of a scalar. So this is like it's not a big deal. Okay. Now the good news is, even though the exponential of arbitrary n by n matrices is very hard, there are some classes of operators, matrices. By now you understand that I use the term to mean the same thing. Okay, so when I say operator, I mean n by n matrices. So the good news I was saying is that there are certain classes like these ones where it's very trivial. I won't say trivial, very easy to compute the exponential. Okay, so when A is a diagonal matrix, you know what a diagonal matrix is because we already covered that. It turns out that the exponential of D is just another matrix, a diagonal one, where the diagonal entries are the exponential of the diagonal entries. This is very nice, right? So this is very, very interesting, right? So this means computing diagonal matrices are very very easy. In fact, it's also very easy. Well, not very easy, very doable, I will say, very easy compared to non-diagonalizable matrices. So if A is diagonalizable, which means, now I'm repeating the definition of what does A mean, if it's diagonalizable, it means this, right? It can be decomposed like this, okay? Then it turns out that the exponential of A is nothing more than this, okay? So you take the exponential of D, we know D is a diagonal, right? And we know that, we know how, because when you do the diagonalization of A, we know how to do that. You can find G, right? So therefore, you can immediately compute the exponentiation of A, okay? So we know that Hermitian operators are diagonalizable, right? So doesn't that mean that then if A is Hermitian, then the exponent of A can also be written like this? This is a question. You don't have to answer it now because you have to think about it. Okay. I see the chat. So Ham property C particularly differs from the usual exponent. Yeah. Yes. So Ham is saying some of this stuff will be, on the lead theory, this is where all these things will become more interesting, especially when we talk about things like one parameter group and these things, these are all like in the context of lead theory, they are much more, they are more natural to discuss that as opposed to the raw, in a raw analytical context. So in the context of lead theory, this becomes more interesting. Indeed, I agree. Thank you, Soham. There's another question in the chat. Property 7. So Nicholas is asking property 7. In which one? Property 7. Where? And this on the thing on the property. Yeah, so it says if A is diagonalizable, so A has to be diagonalizable, then the determinant of the exponential of A equals to the exponential of the trace of A. on the question you wrote, like, is it equivalent or really implies? Yeah, I mean, yeah, you can say if and only if. Also, you can use that. Yeah, because if it's not diagonalizable, then this doesn't have to the thing. Yeah, so I got it. Yeah, yeah. So it doesn't have to hold. So I guess you could say, because if it's not diagonalizable, then this doesn't have to hold. So I guess you could put it that way. You could add if and only if you wish. Now the typo hunters. Let's see who will be the first person to find some something here. As you know, it takes me like 1 or 2 hours. Actually, today I started, even though I finished the slides late. I started like doing them for like 3 hours before or something. But then it's like multitasking. It's very hard to focus. Okay, so. No, the other way. The other way. That's actually very interesting question that I would actually leave that as a challenge. So to everyone to see who can answer that question. So Nicola is asking. Let me go back. So let's see. So he's asking if the other way around is true. If this is the thing, if this implies that A is diagonalizable. So the other way around. That's a very interesting question. So if this is satisfied, if the determinant of the exponent satisfies this, whether that implies that A is diagonalizable. That's an interesting question. Yeah. So I will leave that as a thing, as a challenge. Even not general, like for 2 by 2, for 2 by 2 for 2 by 2 matrices to see. It's a very interesting question. And I think you can answer it for sure. And even have like a counter example. Okay, so what about okay, so we were here. So this is very important. So computing, repeating again, computing the exponential of diagonal is very easy, and computing the exponential of diagonalizable matrices is also very easy. And in quantum mechanics, the most important, or one of the most important operators, which are the hermitian operators, happen to be diagonalizable. So therefore, we can apply this to them in order to help us compute their exponential. Okay. So you start to see why all this notion of diagonalization and these things is playing an important role. Okay. Now, here's the thing: the moment of truth. Hopefully, not the moment of confusion in these things. But I did the best I can in these things. So let's see. So this theorem. I will comment a bit in a way that this is actually a little bit forged, because we could have stated this in a more general fashion, but I chose to cut the chase and go straight to this because this is what matters. So it says, if H is an hermitian operators encoding the Hamiltonian, and we have this map U of t, this is a parameterized map defined like this. So it's the exponential of minus I over H bar times H times T, where T is a real parameter, is a real number. So the claim is that U of T is unitary for all T. Okay. Well, you will be very welcome to if you want to have a go, at least even for a toy example with like a concrete thing to try to compute this to show that this is unitary. Okay, so the claim is that this ut is a unitary, and even we can make even bigger claim. So the bigger claim is that this u of t is indeed the solution for this. Okay, so that's a bigger claim. So because this is unitary, then obviously this is why now you understand why it's called unitary evolution, right? Because the solution is a unitary operator. Okay, so given going back to the thing, for those of you who were not here, if we are given, as I was mentioning at the start when I mentioned axiom 3, is it axiom 4? Axiom 4. So the question was that given an initial state psi of 0, remember this could be psi of t prime or something. I just chose psi of 0 because it becomes more natural, much more easier to put it in the context of a differential equation, where people like to talk about initial conditions and these things. Okay, so the state at a later time is nothing more than just applying this ut, this operator. Okay, so if you know how to compute this, you know how the state of the system evolves. So any state that you are giving, an initial state, you will know how that state will be transformed under this unitary operator. Okay, so let me check. Okay, now the good news is this is why I was saying that we haven't gone through analysis and these things. The thing, a lot of these things that you can compute in this type of stuff. There's a lot of software that can help you do this. But it's good to see the theory behind it, right? Now that for example, another very interesting thing is that this actually there's a general thing about exponentials of Hermitian operators, right? So if you exponentiate a Hermitian operators with I, you will get a unitary. Okay, so that means I assume if you have like the best way to get unitary operators, interesting ones, is to find Hermitian operators and then generate unitaries out of that. Right. So, for example, I'm just trying to imagine those sets of commuting operators. For example, they are all. Imagine if they were all like Hermitian, and then imagine you take them all and exponentiate all of them with this, and then get some sort of a unitary operator. The question is, would you get any interesting unitary operator out of them? If you are doing quantum computing, would you get any interesting quantum gates out of out of these the Hermitian operators? Okay, I'm just asking these questions like they might be like trivial or whatever. It's just for you to start thinking about all these possibilities yourself, and take a piece of paper and start doing it, or get a piece of software and start doing things. Because you now have the theoretical knowledge, you have the theoretical understanding on how these two fundamental type of operators, Hermitian operators and unitary operators, interrelate to each other. Okay, so let me check before I send you the challenge that we have. Okay, no question. Okay. Obviously, yeah, as I was mentioning, if h bar equals 1, then it will be like minus I, like as I was saying on the thing, on the first on the axiom, right? Let me go back there actually, just because I know some people there are more people now joining. So this is axiom 4. So this is Soham wasn't here, so apologies, Soham, if you're having a nightmare reading this. Apologies to any other physicists on the audience. So this is a version of the axiom 4 for the unitary thing. So I now claim that you know what this is telling you, and you know how to compute, how to find the solution for this. That's my claim. Even though we took a shortcut because we haven't gone through like the mechanical way, like going through like the theory of behind matrix operator exponential, because we don't have the analysis nor differential equations we haven't covered. But I think you have enough in order to be able to understand what this is telling you, and also how to use it, right? Because it's very explicit here how to use it, and you know that this is diagonalizable, right? So in principle, you could use that fact in order to compute the exponential of it, right? Okay, so let me go to the challenge. Okay. Okay, let me go to the challenge and then I come back to the chat because I haven't seen the contest that you were discussing. Okay, so here's the challenge. And first of all, for those of you joining, I'm calling this shut up and calculate challenge, not to disrespect or any, the thing is just to highlight that I'm not going through the thing, I'm not going to, enter into the discussion on the physical motivation of this, on the motivation from the physics point of view. So essentially, I'm trying to just run away from physics and just give you something and say, go and calculate, okay? That's why I'm calling it shut up and calculate challenge. No questions asked about physics, just go and compute this. And maybe you can, if you see a physicist, you can ask the physicist, you can have a discussion about what this all means in the physics point of view. Okay, so having said that, so consider a system S and the Hilbert space C2. Remember, C2 is our toy Hilbert space, because it's easy to visualize, right? So, and consider the Pauli matrices again, right? We know this. So the challenge is go and compute the exponential of the Pauli matrices, okay? And then apply the result of the exponential to these skets. I don't know what will happen. I actually never done this, so maybe you might find something interesting. So so this is a challenge. I really recommend you to do this. Even if with the help of software and these things, go and do this. And see. And there's something else I forgot to add here. Go and take the commutators of these of them. And see what else you find. And then apply the commutators to the thing. Okay, this is how you get familiarized with these things. So, yeah. So Saham is giving a tip. That's actually true. Instead of calculating, use their properties to make the calculation. Yeah, you can. Yeah, it's true. Yeah. And now, here's the thing. Actually, you can in this challenge here, suppose that the Hamiltonian of the system is encoded with this. So H equals the identity plus 1/2 times the y operator. Okay. So the question is, we have let's suppose we have the initial states, which is this one. Well, I chose this one because it was the first year. Maybe I should have chosen this one. I don't know. But actually, it's as part of the challenge. Maybe pick different initial states and see what it takes you. So the thing is. The challenge is, what is the state at a later time if the initial state is this, okay? And you are given the Hamiltonian here. So I really challenge you to go and, look at this, and you have been given a concrete Hamiltonian. Whether this Hamiltonian, actually, I chose it like, randomly. This is Hermitian for sure. Yeah, whether it has any physical meaning, then maybe you have to ask a physicist. But this is definitely a Hermitian. Okay. So I hope you are happy with the challenge. Plenty of challenges. And I actually recommend you. I know when I was engaging with Amir, I know you have a channel or a Discord channel where you where you discuss and these things. Maybe you can form a study group or something. Go and discuss all this stuff and come up with maybe challenge each other with other Hamiltonians, construct other Hamiltonians. And the thing is just a practice. It's like I know a lot of you are like programmers. It's like programming. The more you program, the more you become used to it. The more you become better, and the more the stuff sink into your head. Because it's very hard if you don't do practice. You just listen. You go on a few weeks later, everything is gone. So I really recommend you. Now, study materials. I will still recommend this. The thing, it has a lot on matrices and these things. So. And you should be able to, some of the theorems, you should be able to piece them together. They might not be necessarily like stated the way I stated them, or possibly not even stated there, but I claim that with study materials, you should be able to find enough pieces in order to construct a proof for the theorems. Another thing is, thank you to our friend Amir, is I recommend this other resource. I think it's very interesting. It has these interactive stuff, and it's also very, I would say, computer science friendly. So a lot of you are coming from computer science background. The approach taken here, will probably be very, very useful to you. So I really recommend checking this thing out. I will put the link. Amir was the one who gave me the link for this. It's really, I think you do have enough knowledge to read this. It says advanced linear algebra. Well, you are more than advanced to understand this, to be able to follow this book, I believe. So, yeah. So I recommend you this also. I will get the URL and share it with you. In fact, maybe I can. Yeah, I'll share it after. Or Amir, I don't know if you have the URL. I can. Let's see. I can paste it on the chat just for the guys. Yeah, it's okay. I'll put it with the test file on the thing. Okay. Yeah. Thank you, Francisco. So Francisco pasted this on the thing on the chat. So I really recommend. And another thing I want to comment is that if you find any interesting resources and these things that could be beneficial to everyone, like Amir did at this thing, please feel free. In fact, I've added Amir and Aditya as collaborators in order to help curate, and I think Aditya offered to build a GitHub page or something to make the resources a little bit more easier to find. So thank you for that also, and thank you, Amir. If the rest, you want to contribute and share stuff, you can coordinate with Amir and Aditya. And yeah, I really think it's very useful, because obviously I don't have time to go and create multiple stuff. I will probably miss most of the useful stuff that are out there and free. So it's good that we have you guys. You are coming up with suggestions, on things that might be useful to the rest to learn. So yeah. So thank you so much to Amir and Aditya for offering the thing to help with this. So with that, I don't have anything else to think. I actually I was going to create something on physics, but I don't have anything. I couldn't find, so I would just recommend stick with the Susskind that I recommended before, and the other Perimeter Institute lectures on physics. Next week, I will definitely have more other extra recommendation on the physics side for you. It's just this week I've been a little bit all over the place, so I didn't have time to look at the materials and make any suggestion. Okay, so with that, yeah. So if you need any help, definitely you need to you can ask Soham. I'm sure Soham will give a lot of a useful recommendation on the physics side in order to help you bridge the gap, right? In order to see how physicists, think about these things, right? So, because it's not easy, really, on the thing, So, one thing is learning the mathematics, the thing. The other thing is also the other challenge is to how it connects to the physics of the physics side of things. So yeah. So let me go back to the questions. I think this is the last slide. I don't think I have anything else to say. Okay, so Soham is also recommending Susskind's book. Yeah. And his lectures also, they are very, it's also very funny. He has a very good sense of humor. So on the physics side, definitely the thing. So there's one, I think the book, actually, the quantum mechanics, the theoretical minima, I think the lectures, he has lectures on that. Yeah, for sure. Okay. So I have a question from George saying, so psi is a mapping from Hilbert space to real numbers. Which question is this? I'm trying to remember. Is it to do with the Schrodinger equation? Well, I guess the best way to see it is, yeah, you can view it like, because it's indexing, right? It's indexing the size. You can view it like indexing the parameter t, being an indexing set for the Hilbert space, I guess. Maybe that's a little bit sloppy, but yeah. Yeah, I think that's the simplest. The indexing is, I guess, the simplest. Because you can index. Normally, in the thing, we are only used to thinking about indexing unless you are in pure mathematics with like finite set stuff. But you can also index stuff with infinite sets. Why not? So the indexing set doesn't have to be finite. So. Amir, I guess the question that you asked about the Dirac notation, which I was scared of answering. I think Soham already answered this, right? I was scared because I'm afraid of the Dirac notation. It's a nightmare, because I always make mistake with it, because it has all these fancy rules, you put the bracket this side and this thing, and then you take the, it's like, yeah. Okay. Was there any other question that I missed, Soham, or not really? Yeah, so. Yeah, so Barry's saying physicists insist that the Dirac notation is easier. Yeah, I agree with you. I don't know why they say that. If anything, it's like a confused, confused to like. Maybe Soham will disagree because he's used to using it, right? Once you are used to something, it becomes easy to think. But for me, it's like a unnecessary confusion, right? Like last time, when I switched the size, apparently I should, one of the size I switched their order, so it's it's like. So yeah, physicist notation is for me especially the Dirac notation is very confusing and often very ambiguous. But nevertheless, they say it's very easy for them to do calculations. So yeah, that's why I try to avoid them. But at the same time, it's good to mention them. I mentioned them. I hope. I did my best to try to give you the flavor of the Dirac notation, because the test books are full of these notations, so you're not scared when you see them. But it's mostly about practice. So the more you practice, this is something. This practicing Dirac notation is to do with the reading or watching physicists. Mathematicians, you will not learn the Dirac notation with mathematicians. Okay. Yes, the Dirac, the bra. Yes. So Amir is saying interesting to relate linear functional to Dirac. Yeah. So I hope I don't know how many of you were confused with the Dirac notation, but are probably less confused now after going through this foundation module. I'm just curious. It's not just that it's important anyway. I must say I'm also less confused because I had the opportunity now to look at Dirac notation because I never really look at it. Yes, Barry saying repeated exposure helps. Yeah, this is the thing, the more you get exposed, you see it, the more it becomes familiar with you. Obviously, if you are a working mathematician, you don't see this often, so you forget. If you are a working physicist, obviously, especially in this case, theorist, like Soham, you see this every day, and it's like it becomes a yeah. Yeah, so Ham is saying also we are more interested about practical calculations. Yeah, so I guess it's more from a practical point of view, indeed, as opposed to abstract and a formal, rigorous thing. So yeah. So George is saying, I find it helpful that you use mathematical notation and translate to and from Dirac. Yeah, I try to do my best, and I thank Soham for being around for correcting in times where the thing I got it wrong. But yeah, because you can easily it can easily be very confusing if you don't if you don't see the thing put it into the context. So yeah, so I hope that has been very useful to all of you guys again. Okay, I know we are running over time, so I don't want to take much of your time. Is there any other question that you want to ask in respect to the actual module? So let me just go back again. If you want to leave, those who want to leave, it's okay. You can just disconnect. That's fine. But yeah, so we are in. So the next, if we stick to the plan, the next session will be the last session. But I still feel maybe we need another extra session. I don't know. We'll see. So what I want to cover next will be like tensor products. Are we meeting? So Amir is asking, we are meeting next week. Yes. So it's the last session as of the schedule here. Or do you guys want? I'm happy also for if most of you want to reschedule because it's the last session. It meant to be the last session anyway, and I think I will be able to cover what I want to cover. Again, the tensor product is the other axiom we want to go through for a composite system. Anyway, that's the plan. And with the tensor product, it will be very interesting because I have to be very careful because if we start in the wrong footing, the abstraction will just overshadow. So maybe we'll do the other way around. Like we'll start with concrete, practical for those of you who are new to these things. So you see how to use it, and then in the final part of the session, we go through the abstract, the formal stuff. So then, if you don't understand the abstract stuff, it doesn't matter anyway because you know how to use it. So that's the plan. Because if you start with in the wrong footing with the tensor product, it's like it can be very annoying from my experience interacting with the people in this thing. So maybe we'll just we'll start with the concreteness as opposed to start with the abstraction, and then we'll start the other way around. Start with the concrete example using our toy example C2, and then at the end we give a very abstract definition of tensor product, and then if you don't understand it, that's fine. You know how to use it anyway, so it doesn't matter. Okay, so if you don't have any question, maybe we should leave it here. unless somebody have a last minute question, you have, I'll give you 20 seconds to think about something. If not, well, we catch up next week. Okay. Okay, so thank you guys, and well, we catch up next week then. And thank you, Soham, again. Thank you, everyone. Thank you, George, Francisco, Nicolas, Claudia, Soham, everyone, Amir. I'll see you next week. See you.